Hey y'all, welcome to Miss Clarke's chemistry class. This is the 6th lesson in a series of lessons on nuclear chemistry. Have you been waiting for a lesson about how to calculate using half-life? Now, I'm going to be super honest with you just right up front. I don't use the formula, so if you're looking for a lesson to help you with that formula, I'm not your girl, unfortunately. I like to use a little bit of logic to figure it out, so I just wanted to be honest right up front. Didn't want you to waste your time. So you're definitely going to need your notes, periodic table, calculator, my favorite, math. The math in this unit, though, super simple. Promise. All right, let's get started.
So let's just jump right into what the definition of a half-life is. And half-life is the time it takes for 1/2 of atoms to decay. Remember, we're still talking about nuclear chemistry. We're still talking about the transmutation of those radioisotopes. Those atoms that have nuclei that are too unstable because their nucleus is too big, or the ratio between protons and neutrons are just out of whack, and they start to decay. The half-life is going to tell us how long it takes for 1/2 of the atoms to decay to a new element. If we started with the chunk of element, and all of these dots represent the same type of atom, so the blue dots represent a whole atom with its protons, neutrons, and electrons. The half-life is going to tell us how long is it going to take for 1/2 of those atoms to mutate, to decay into a different element. So we would have half of the elements to be something brand new. Half is still the original element, these blue dots, but half is a brand new element. We've been talking about radioactive decay and how the atoms mutate into other atoms. This is called transmutation. But the half-life is going to tell us how stable something is. The shorter the half-life, the more unstable the nucleus was to begin with. So let's look at some examples. You're going to need your periodic table and your calculator. If you don't have either one of those, make sure and stop the video. Go get those right now. So let's look at carbon-14. Carbon-14 has a half-life of 5,730 years. Carbon-14, it is radioactive, it is emitting radiation, but it takes 5,730 yegoing for half of the sample of carbon to decay. Using the half-life, we can figure lots of things out. So that's what we're going to practice. I'm going to show you a variety of different problems that you could be asked and how you would utilize half-life to figure out the answer. There is a formula for this, and if your teacher's giving you the formula, my lesson's not going to help. I don't like to use the formula. I like to use a little bit of logic. Okay, so let's look at this first example. How many years would it take to go through 3 half-lives? Now, this one's probably the most basic question, especially since I already told you how much 1 half-life is. So if 1 half-life is 5,730 years, how many is 3 half-lives? We need to know, we're just going to multiply. So I'm going to go ahead and put that in my calculator. We get 17,190 years. So for carbon-14 to undergo 3 half-lives, that is going to take 17,190 years. I know half-life is still a little shaky for us. Let's keep working through some more examples so we can see all the useful information that we can get from understanding the half-life. Still going to use carbon-14, still has that same half-life, 5,730 years, but I wanted to look at it at a different perspective. What percentage of a sample will be present after 3 half-lives? So we still have that 3 half-lives, but I want to know about a percentage. Okay, so don't let that freak you out. We're going to start with 100%. After 1 half-life, we would only have 50% left, right? Half-life, half is left. So after 1 half-life, half is left, 50%, that's half. Okay, so now after the second half-life, what's half of 50? 25%. So after the second half-life, we only have 25% of the sample left. But we wanted about 3 half-lives. So what's half of 25? 12.5%. That's our answer. It didn't really matter how much we started with. It didn't really matter if we knew what the sample was. It really didn't even matter what the half-life was. When we're asked about percentages, you would need to figure out how many half-lives and then count down just like I just did. Now, this is a very simplistic form of this question. There could be questions where you have to figure out how many half-lives and then go through this process. We're going to get to the problems like that. As you're working through problems on your own, You might realize that I'm giving you all of the tools, but you might have to put two of these pieces together. Still going to talk about carbon-14. Its half-life is still 5,730 years. This time I'm going to give you a little bit more information, and we're going to actually work out a problem. If I start with 100 grams, how many grams are going to be left after 3 half-lives? Okay, so we know we've got 3 half-lives. Okay, so I'm going to start with 100 grams, and I've got to go through 3 half-lives. So after 1 half-life, 50 grams is left because there's only half left. So half of 100 is 50. After the second half-life, 25 grams is left. And then after the third half-life, 12.5 grams are left. Now, I did go a little bit quickly through that problem, and it's only because the last problem we started with 100, even though it was percent. This problem we're starting with grams, but it's still 100. So those numbers looked the same. We broke that down 3 times because we had 3 half-lives. So if we started with this 100 grams of carbon-14, after 3 half-lives, and we figured that out a second ago, that was like 17,190 years. Now that's not really important for this problem. I'm just kind of wanting to close the circle for you just a tiny bit. So if we start with 100 grams, after this many years, we're going to have 12.5 grams left. Let's try another example. If the half-life of an isotope is 3.2 days, see how different that is? This is very unstable. How much of a 600 gram sample would be left after 13.8 days? Now this one's a little bit more complex. We've got a little bit more information, and we're going to have to work through 2 things. Now we were given the half-life. I'm going to write that down actually. I'm going to do T 1/2 because a half-life is time. And I've got 3.2 days. I'm starting with a 600 gram sample. And what we're being questioned about is how much is going to be left after 13.8 days. So, as always, we need to figure out how many half-lives occur. That's always step 1. How many half-lives occur? So let's think about that. If every half-life is 3.2 days, how many 3.2 days are there in 13.8 days? That is just simple division. 13.8 divided by 3.2, that's going to tell us how many half-lives occur. I'm getting 4.31. I'm going to round that to the nearest whole number and call that 4. 4 half-lives. So if we start with 600 grams, we're going to cut that by half. So 600 cut in half, 300. That's the first half-life. 300 divided by 2, cut in half, 150 grams. That's the second half-life. 150 cut in half, that's 75. That's the third half-life. Here we are, the fourth half-life. That's what we're wondering about. And I'm getting 37.5 grams. So let's go back and look at this problem again. We were given the half-life. We were given how much sample we started with. And we were told how many days we're letting this decay. So we took our total days and divided it by our half-life to figure out how many half-lives occurred. Then we just start with our sample and we cut that in half for this many half-lives. And we get our 37.5. Let's look at another problem. If the half-life of carbon-14, there we are with that carbon-14 again, 5,730 years, how much of a 50 gram sample would be present after 45,720 years? Now this problem is exactly like the one we just worked. So I'm going to want you to press pause, work through this problem, look back at the last example if you need to. Get your answer, push play, and let's see how you did. Again, step 1, always get how many half-lives are occurring. How many half-lives are occurring? So we're going to take our total time and we're going to divide that by our half-life to see how many half-lives fit in that 45,000 year frame. And I'm getting 7.97, so I'm going to count that as an 8. 8 half-lives. So we've got a 50 gram sample. We're going to cut that in half to 25. That's our first half-life. We're going to cut that in half to 12.5. That's our second half-life. We're going to cut that in half, 6.25. That's our third half-life. We're going to cut that in half, 3.125. That's our fourth half-life. Cut that in half. That's our fifth half-life. Cut that in half. You see where I'm going. We're just going to keep cutting it in half 8 times. Whew, 0.195 grams. Can you see that? 0.195 grams. I hope I didn't get off the page right there. Kind of had to squish it together down there at the bottom to get 8 full half-lives in. I hope that's what you got, 0.195 grams. Let's look at a couple more examples. Okay, so let's look at this example. Strontium-90 has a half-life of 28.8 years. Not quite as stable as that carbon-14, is it? How long will it take for a 250-gram sample to decay to 15.6 grams? Now, this problem is worded completely different. We're given grams twice, we're given the half-life, but we're not given total days like we were in those last two problems. That's okay. The problem is still going to start with the same first step. We need to answer this first question, how many half-lives? How many half-lives? We're going to work this problem completely backwards. We're going to take our 250 grams and we're going to see how many half-lives it takes to get to 15.6. So after the first half-life, we're at to 125. Cut that in half, we get 62.5. That's our second half-life. Our third half-life, 31.25. And then our fourth half-life, we're getting 15.63. That seems close to me. It took us 4 half-lives. We're not done because it asks, how long will it take? Well, for one half-life, we know it's going to take 28.8 years, but we have 4 half-lives. So I'm getting 115.2 years. If you start with a 250-gram sample, it's going to take 115.2 years for that sample to decay down to 15.6 grams. Now remember, I'm saying decay, that's because we're changing to a different element. It's not like it's just disappearing. Just want to make sure and point that out. Let's look at my last example. How long will it take for a 50-gram sample of carbon-14 to decay to 3.5 grams if the half-life is 5,730 years? This problem is just like the one we just worked. Press pause, work through it, meet me back, and let's see how you did. So again, always, how many half-lives? How many half-lives? So let's start with our 50. Let's cut that down to 25. That's what our first half-life is. 12.5, second half-life. 6.25, third half-life. And in this next half-life, I'm getting 3.125. We're going to call that close enough. 4 half-lives. I hate that I found so many problems with 4 half-lives, but that's okay. 4 half-lives. We know that each half-life is 5,730, but we need 4 of them. 22,920 years.
Dividing numbers by half, not that big of a deal, right? The only thing is you just have to figure out how many times to divide by half. That's where the logic comes in. We don't need a formula for this. Well, I hope that helps. Until next time, bye y'all.